This is a presentation of the article IMU alignment for smartphone-based automotive navigation, which also was presented at the IEEE conference on information fusion in 2015. My name is Johan Wahlström and I was the main author of the article. My co-authors were Isak Skog and Peter Händel. If you have any comments or questions, I'll be very happy if you email me on the address that you see on this slide. In this video, I'll show you how to utilize inertial measurement units in smartphones for automotive navigation when there is no a priori information on the orientation of the smartphone with respect to the vehicle. Although this is not the first proposed solution to this problem, I believe this method has a number of advantages. The primary one being that the algorithm is a very straightforward extension of the standard method for GNSS-aided inertial navigation. This means that it should be easy to understand for anyone with previous experience of these types of filters. At the end of the video, I'll show you where to find MATLAB code and also show you how to run it. Let me give you a short motivation for why we would like to use smartphones for automotive navigation. First, it's very cheap as compared to other solutions. At least now, given that the smartphone penetration rate has become so high all around the world. Second, it's user-friendly. The only requirement on the driver is that he or she downloads an app. And third, we have many possibilities for user interaction. We can communicate with the driver and the passengers using either audio or visual means, and we can even offer services to the driver when off the road, since he will usually carry his smartphone with him when leaving the car. Notable examples of smartphone apps which employ some sort of smartphone-based automotive navigation include Waze and Uber. There are three types of data sources that we will use. The first one is the GPS receiver. Here I use the more general term GNSS. GNSS receivers in today's smartphones will provide us with measurements of the smartphone's three-dimensional position and also of the smartphone's speed and course in the horizontal plane, which is tangential to the surface of the Earth at the current position of the smartphone. We will also use accelerometers, which measure three-dimensional specific force, and gyroscopes, which measure three-dimensional angular velocity. I will begin by presenting the standard method of GNSS-aided inertial navigation. First, let us define a navigation state, which includes three-dimensional position and velocity, as well as attitude. Since all sensors are in the smartphone, we should interpret this as quantities of the smartphone. Second, we define an input vector which includes the quantities measured by the inertial measurement unit. We are now ready to formulate our state space model. The state equation, equation 1, describes the time development of the navigation state. These equations are also called the navigation equations. And the measurement equation, equation 2, describes how the GNSS measurements depend on the current navigation state. We can now implement an extended Kalman filter based on this state space model, and that would be what we typically call a GNSS-aided inertial navigation system. To summarize, this filter takes IMU and GNSS measurements as input, and then provides us with estimates of the navigation state and of the IMU bias. All this is nice, however, it only means that we can estimate the navigation state of the smartphone. What we are actually interested in is the navigation state of the vehicle. In order to estimate the navigation state of the vehicle, we will begin by making two assumptions. First, I assume that the vehicle and the smartphone have the same position. This is typically a feasible assumption since the GNSS position errors often are larger than the length of the vehicle, which in some sense is the maximum error that can be introduced by this assumption. Second, we assume that the vehicle and the smartphone had the same velocity. This is justified since the speed of the vehicle typically is much larger than the speed of the smartphone with respect to the vehicle. Given these two assumptions, the GNSS-aided inertial navigation system, which I presented before, will provide us with estimates of both the vehicle's position and of the vehicle's velocity. What is left is to estimate the attitude of the vehicle. To give you a feeling for what this really means, let us study the following figure. What I have already showed you is how to estimate the attitude of the smartphone. This is equivalent to estimating the relation between the coordinate frame of the smartphone, S, and some reference frame, say T, a tangent plane frame. What we are actually interested in is the vehicle's attitude. That is the relation between B, the vehicle's body frame, and T. Now, note that if we want to know the relation between all of the coordinate frames, it is sufficient to estimate any two of the three possible relations. This is just a commonly known property of rotations. What I will do is to continue estimating the relation between S and T, and in addition also estimate the relation between S and B. So we construct an augmented navigation state, Z, which includes the old navigation state and the orientation between S and B. Our new state equation will be composed of the standard navigation equations for the old navigation state, and for the new states we will use a random walk model. More precisely, I will model the Euler angle errors to develop according to a random walk. To make this augmented navigation state observable, we need new measurements in addition to the GNSS measurements. Therefore, we will use two typical characteristics of vehicle dynamics. First, we note that the vehicle's velocity tends to be roughly aligned with the forward axis of the vehicle frame. This information can be incorporated into the filter in several ways. Here we chose to introduce pseudo measurements of zero velocity in the lateral and vertical directions of the vehicle frame. Second, we will use the fact that the vehicle's roll angle tends to be close to zero. We incorporate this information in a similar way, that is, by introducing pseudo measurements of zero roll angle. It is important to note that these two measurements does not mean that we constrain the estimates of, for example, the velocity in the lateral and vertical directions of the vehicle frame to be zero. We merely use typical vehicle dynamics to extend the observability of the system. Now we can summarize our new state space model. The state equation includes the old and familiar navigation equations, and in addition we have modeled the relative orientation of the smartphone and the vehicle to develop according to a random walk. The measurement equation includes not only GNSS measurements, but also pseudo measurements of velocity and pseudo measurements of roll. Just as before, it is possible to implement an extended comma filter based on this model, and this is the estimation framework which was proposed in this article. First, the presented estimation framework was applied to a simulated vehicle trajectory, constructed to emulate typical vehicle dynamics. Here you see both the horizontal movements of the car and the vehicle speed. IMU and GNSS errors were assumed to be white and normally distributed, while the IMU bias and the smartphone to vehicle orientation were simulated from uniform distributions and were assumed to be constant over the complete trajectory. Here we see both the theoretical standard deviation and the root mean square error of the estimated vehicle roll and pitch angles. And here is the corresponding graph for the yaw angle. As can be seen, the root mean square error is in the order of 2 degrees for each Euler angle, We also apply the proposed framework to real-world data collected from 3 smartphones. The time average root mean square errors are displayed in the table. Just as before, these are in the order of 1 or 2 degrees. As has been shown in previous papers, pseudo measurements of velocity will reduce the position drift during GNSS outages. Here we see that this also is the case, even if we do not know the exact relation between the smartphones and the vehicle's coordinate frames. Typically, we will after a GNSS outage of 1 minute have a position drift in the order of 250 meters. To conclude, we first noted that the standard GNSS-aided inertial navigation system implemented on a smartphone will not provide us with estimates of the vehicle's navigation state. What we then did was to assume that the smartphone and the vehicle had the same position and velocity. Moreover, using pseudo observations of velocity and of the roll angle, we showed how to estimate the attitude of the vehicle. The accuracy was in the order of 2 degrees for each Euler angle. So now I'll give you a short introduction to the MATLAB code. First, you want to go to this website, and you'll find a link in the paper. And then you want to download IMU alignment code. And after extracting the files, you will see 2 main files. The first is for running the algorithm on the real-world data, and the second is for the simulations. Studying the real-world data, you load the data, and this is both reference data as well as measurements from the 3 smartphones. You then run the algorithm on the 3 smartphones. If you want to study the position drift, you should also run the standard inertial navigation system. And below, you will find all the plots and quantities displayed in the paper. Most of the variables have the same names as in the paper. The main file for the simulations is very similar. You first load all data, and this includes the true vehicle trajectory, and then in each simulation iteration you generate a constant smartphone to vehicle orientation, you generate GNSS errors, and you generate IMU errors. So that was it for this video. Let me know if you have any questions. Thank you.